dspy employs a declarative signature-based approach to define modular LM behaviors, where dspy, signature, serves as the foundational abstraction for specifying input-output contracts with semantic field naming. This particular implementation demonstrates how custom reward functions and the dspy.Refine module can be composed to enforce factual accuracy through iterative self-correction. You're about to see how a factuality judge signature gets instantiated as a chain-of-thought module, then integrated into a refinement pipeline that automatically evaluates and retries predictions until achieving perfect factuality scores. The setup will reveal how input fields flow through prediction objects, how Boolean outputs drive reward calculations, and how the refine mechanism orchestrates multiple attempts with threshold-based termination.
Import dspy. Class factuality judge signature. Determine if a statement is factually accurate. Statement str equals dspy input field. Is factual, bool equals dspy output field. Factuality judge equals dspy, chain of thought factuality judge. Def factuality reward args pred, dspy, prediction float. Statement equals pred answer. Result equals factuality judge statement. Return 1 if result is factual else 0. Refined ka equals dspy, refine. Module equals dspy, chain of thought question answer. N equals 3. Reward fn equals factuality reward. Threshold equals 1, 0. Result equals refined ka question equals tell me about Belgium's capital city. Print result, answer.
This code demonstrates a factual accuracy refinement pipeline using dspy's advanced signature system and custom reward functions. The pattern combines a class-based signature with input-output field declarations to create a structured factuality judge, then integrates it with the refine module for iterative quality improvement. The factuality judge signature uses dspy, input field, and dspy, output field, to explicitly define the input statement and Boolean output, creating a clear contract for the LM. This structured approach enables the factuality reward function to evaluate predictions by checking the isFactual field, returning a binary score. The refine module then uses this reward function to iteratively improve answers, stopping when it achieves perfect factual accuracy, threshold equals 1, 0, or exhausts attempts n equals 3. This approach trades off computational cost multiple LM calls for reliability, particularly valuable when factual precision is critical. The class-based signature provides more explicit control than string-based signatures, while refine offers better feedback incorporation than best of n. The binary reward function simplifies evaluation, but requires the factuality judge itself to be highly reliable, as false negatives would incorrectly penalize valid answers. Let's break it down.
Import dspy.
Imports the dspy framework, providing tools for declarative programming with language models through signatures and modules.
Class factuality judge signature. Determine if a statement is factually accurate.
Defines a dspy signature class named factuality judge that declares a task for determining factual accuracy of statements. The docstring specifies the module's purpose, while inheriting from dspy, signature, establishes it as a declarative specification for LM behavior. This creates a reusable signature that can be assigned to dspy modules to perform factual verification tasks.
Statement str equals dspy input field.
Creates an input field named statement with string type annotation using dspy's input field class. This defines a typed input parameter for a dspy signature, where statement will accept string values when the signature is used in a module. The type hint str indicates the expected data type, while dspy Input field initializes it as a dspy input field that can be processed by the framework's optimization mechanisms.
Is factual. Bool equals dspy output field.
Declares an output field named isFactual with Boolean type in a dspy signature, indicating this field will contain a factuality assessment result from the module's execution. The dspy output field constructor creates a typed output specification that the dspy framework will use to validate and structure the module's return values.
Factuality judge equals dspy. Chain of thought factuality judge.
Creates a factuality judge module using dspy, chain of thought, with the factuality judge signature. This sets up a language model module that will perform factuality judgment tasks using chain of thought reasoning, where the LM generates intermediate reasoning steps before producing the final answer. The module is now ready to be called with inputs matching the factuality judge signature.
Def factuality reward args pred. dspy prediction float.
Defines a function named factuality reward that takes two parameters, args and pred, a dspy prediction object, and returns a float value. The function is designed to evaluate the factual accuracy of a prediction, likely by computing a reward score based on the prediction's content.
Statement equals pred answer.
Extracts the answer field from the pred prediction object and assigns it to the variable statement. This retrieves the output value generated by a dspy module's execution, where pred is a prediction object containing the module's results.
Result equals factuality judge statement.
Calls the factuality judge function with the statement as input and assigns the returned result to the variable result. This is a straightforward function invocation where factuality judge processes the provided statement and returns an output, which is then stored in result for further use.
Return 1 if result is factual, else 0.
Returns 1 if the result object's isFactual attribute is true, otherwise returns 0. This converts a Boolean factuality check into a binary score where factual results receive the maximum score of 1 and non-factual results receive 0.
Refined Ka equals dspy. Refine.
Creates a refined Ka instance of the dspy refine class, which implements an automatic feedback loop for iterative improvement of language model outputs. This module will attempt multiple generations, providing detailed feedback after each unsuccessful attempt to guide subsequent runs toward better results. The variable refined Ka now holds this configured refiner ready for use in a question answering pipeline.
Module equals dspy. Chain of thought question answer.
Creates a dspy chain of thought module configured with a signature that takes a question input and produces an answer output. This module will use the chain of thought prompting technique when processing inputs, breaking down reasoning steps before generating the final answer. The signature defines the expected input-output structure, while the module handles the specific prompting strategy.
N equals 3.
Assigns the integer value 3 to a variable named n.
Reward Fn equals factuality reward.
Assigns factuality reward as the reward function for evaluating predictions, which will be used to score and optimize the module's outputs based on factual accuracy.
Threshold equals 1, 0.
Assigns the float value 1 to a variable named threshold.
Result equals refined Ka question equals tell me about Belgium's capital city.
Calls the refined Ka module with a question about Belgium's capital city, passing the string, tell me about Belgium's capital city. as the question parameter. This triggers the module to process the input and generate a response, which is then assigned to the variable result. The refined CA module likely uses a refined or optimized approach, such as iterative feedback or multiple attempts to answer the question, as suggested by its name and the context of dspy's refine functionality.
Print result, answer.
Prints the value of the answer attribute from the result object, which is a dspy prediction containing the output of a module execution. This displays the generated answer or response from the language model after processing the input through the defined dspy pipeline. This implementation showcases dspy's declarative approach to building reliable LM pipelines through signature-based contracts and iterative refinement. The factuality judge signature establishes a clear input-output contract with semantic field naming, while chain of thought enables structured reasoning for factual verification. The reward function bridges these components by converting Boolean factuality checks into numerical scores that drive the refinement process. The refine module then orchestrates this feedback loop, automatically retrying predictions until achieving perfect factual accuracy or exhausting attempts. This pattern trades computational overhead for reliability, particularly valuable when factual precision is critical. The class-based signature provides explicit control over the factuality judgment task, while the binary reward function simplifies evaluation, but requires the judge itself to be highly reliable to avoid false penalties. The composition demonstrates how dspy's modular components can be combined to create self-correcting pipelines that iteratively improve output quality based on custom evaluation criteria.
The refine module polishes answers 3 times. Yet the mirror of truth remains fogged by its own